Greetings and welcome to a new video about 2 degrees of freedom controller design. This will be our example number 5. In this example we will again look at the calculation step by step and we will verify these in simulations using MATLAB. So we have the following open loop system given. We have the G open loop system and this is the configuration we will use for this 2 degrees of freedom control system. We have the controller 1 and the controller 2, GC1 and GC2, and we have the plant here G. In addition, we have 2 inputs, the reference R and also the disturbance from outside, which is then here D, and our output is Y. So the plant is given by this expression 6 over s plus 1 times s plus 6. This is the transfer function of the plant. And these are the specifications for this example. And what we see is, again, the response to a unit step disturbance must have a small peak and also needs to settle to 0 in less than 2 seconds. Again, this is similar, or actually exact same as in the previous examples. We also see here in the third specification is that the steady state errors are 0 for step, ramp, and also the acceleration reference input, and this is also the same as we did in the previous examples in this 2 degrees of freedom control design. The change in this example is about the response to a unit step reference, and the overshoot here must be maximum 2%, which is the lowest so far, and the settling time is 0.4 seconds. So these are 2 quite challenging specifications. So let's see what we can do here. Now, looking into the solutions, we will start always with the closed loop transfer function for this configuration. And now, of course, we take the reference to output separately and also the disturbance to output separately. Now, the transfer function we have for the reference to output this y over r, and we have discussed this in great detail also in example number 1 in this series about 2 degrees of freedom control design. Disturbance to output, so only considering disturbance and not taking into account the reference, then the closed loop transfer function will be given by this expression. What you see here is that this transfer function and this transfer function has the same denominator. It means they have the same characteristic equation, which is of course required for later determination of the dynamics. Step 1 is first considering the disturbance only, because this transfer function, which considers only the disturbance to output, has in the characteristic equation just the controller 1 and only actually in a total transfer function. So we start with that and we consider only disturbance. In that case, we then assume that the controller 1, GC1, is a PID controller given by this expression. In fact, a PID controller has a pole at origin and 2 zeros that can be different. It can be also at the same location. In this case, it is chosen to be at the same location, so we have a double 0, and we have a gain, of course, of the PID controller, and we have again the pole at origin. Now, the location for this situation is then 1 plus the loop transfer function is equal to 0. That is the root-lowest equation. The loop transfer function is actually the GC times G, which is actually, you can also say 1 plus this, which is actually shown here. So the characteristic equation equal to 0 is the root-lowest equation. Now, substituting what we have for the controller and also our plant, you will get this expression. Even more simplifying this, such that we have only one fraction, you will get this expression. And we will then later see how we determine that small letter a and also the k1 for the PID controller. From the specification, we know that the overshoot must be 0.02 or 2%, so MP as a scalar value will be then 0.02. Going from here to the damping ratio, you will get this value. This is a formula we have also used in many other videos, like root locus design of a controller. So we have then 0.78 for our damping ratio. The settling time is giving us 0.4 seconds or 400 milliseconds. Again, using this formula for over the settling time for 2% criterion, will give you the sigma d, which is the real value of our design point, what we will determine, or it's also called the absolute damping. Then, since we have the real value, we also need the imaginary value, which is then omega d, and omega d is called the damped radian frequency. That is then the sigma d times the tangent of an angle, and that angle is determined by the arc cosine, so inverse cosine of this value, which is then the zeta of it, or the damping ratio. Now, when you fill in the given values, or we have determined, we get 8.03 radians per second. Now then the design point is given by this expression, which is a minus sigma d plus j omega d. You substitute everything which you have, and you will get this minus 10 plus j 8.03. This is a really important step. Again, the design point we have here, and we will use this for later calculations for the A and also for the K1 for the PID controller. Now, we know that we have two conditions we need to meet for our root locus equation. One of them is the angle condition, the other one is the magnitude condition. First, we start with the angle condition, and before we move on with the actual calculations, let's make a sketch, and this is the real and the imaginary axis, and this is the complex thing. We will also give our PM. Now PM is actually shown here. You can see the PM minus 10 and J 8.03. This is the root locus equation we have determined, and from here you can see the poles and the zeros. One of the poles is at the origin at 0. That is the PID pole, and that will contribute some phase, which is then determined from this location up to the PM, and that phase is called phi 1. We have also the phase contribution by the pole at minus 1, and also this will make an angle using this formation. We have also the pole at minus 6, and these two are the plant poles, which is from our open loop system or our plant. And this will also make an angle, which is called then phi 3. In addition, we have of course the 0, so this is then phi 3, and this A, which is of course the PID 0, is a double 0, which is located at minus A. We don't know yet where it is. It is maybe here, it may be there, maybe on the left side of this vertical dotted line. We will determine that shortly. The angle condition for this situation is all the poles plus all the 0 phase contribution must add up minus 180 degrees. We know the phase contribution of the poles are negative and the phase contribution of the zeros are positive. So you can see minus phi 1, minus phi 2, minus phi 3, because these are all poles. And we have a double pole, and it is also positive because double 0, and we have also which is positive. That's why we have a plus and 2 for the double 0 of the PID controller. Now let's then determine what the phi 1 and phi 2 and the rest of the values are. Now phi 1, again, this is the PID pole at the origin. Phi 2 is the phase contribution by the plant pole at minus 2. Then phi 3 is the phase contribution of the plant pole at minus 6. And this phi A is the phase contribution of the double 0 by the PID controller. Phi 1 is this, you can calculate using this expression. You can see I have done 180 degrees minus an angle, and this angle is this sharp angle here, which is then less than 90 degrees, between 0 and 90 degrees. This complete half circle is 180 degrees, and you subtract actually this sharp angle, and you will get what you require for phi 1. This is the expression. This is the height, and this is the distance. So you take actually the arctangent of that ratio, you will get this angle, and you subtract that from 180 degrees. That will give you 141 degrees. In a similar form, you can do that for phi 1, phi 2, and phi 3, and you will get this result. You can see 10 minus 1 is this distance, and 10 minus 6 is this distance. So you will have another ratio because this distance between the -10 and also the location of the pole will change. That's the only change actually here in this expression. Now let's then substitute what we have. So we've substituted this in this expression, the determined values here, and you will get this expression. And when you calculate phi a, which is then the phase of 1, 0, will be then 107. So for each 0, we need a phase contribution of 107 degrees. So this is then the diagram or the picture for our phase for our 0. And again, how do we know it is here and not at the left side? This phase is larger than 90 degrees, so between 90 and 180 degrees. In order to have that, it must be at the right hand side of this, dotted line, because when you have an angle which is larger than 90 degrees, you need to have it like that, because if you have it here, that angle will be a sharp angle. It will be then between 0 and 90 degrees, which is not possible for 107 degrees. That's the reason. Now, using geometry, we can then calculate the location of A, because that's the next step. We know this angle, but we don't know yet this angle. That can be used now, and this triangle has a right angle here, and you can use a tangent formula, which is then tangent of that angle is then this height divided by this distance, which is then 10 minus A, which is shown here. So this angle is, substituting value will give you then 173 degrees, 73 degrees, excuse me, will be then this expression. And if you now do the math for A, you will get 7.54. Now we have now the PID controller, one of the parameters actually, because the A was an unknown, also the K1. We have now one unknown determined. Now we have the controller one so far as given by this expression. All right, the next step is then the magnitude condition. So we have done now the angle condition. Let's move on to magnitude condition, which is then using the Root-Logos equation again. And we calculate now the PID controller K1. So again, the Root-Logos equation, we set up what we have so far. So only unknown is the K1, given here specifically as a green, in green. So the K1 is also expressed in different forms. So you can place this 1 to the right hand side and divide by this coefficient of K1. You will have this expression. You can see the minus sign here, but that doesn't matter. It is really the magnitude. Now, in order to calculate the real value of K1, which is the actual value of our K1 parameters, we need to evaluate this expression at the design point we have determined. PM is equal to -10 plus J 8.03. Now we have done that here. You can see that we have said that this absolute value must be evaluated at PM, which is also true for the right hand side. We substitute the value, so for every place where you see a S, you just substitute this value for the PM, which is then our design point, because you're given here actually in red. You can simplify this because you see here -10 and +1 and -10 and 6, etc. So you will get this one, and then you calculate for each parentheses the length. You're using this square root of the real squared plus the imaginary value squared. This is a straightforward calculation, and you will get then the result is then 3.3 approximately, or 3.28, closer to that. Now we have the A, and we also have the K1. That means the PID controller, GC1, the first controller, will be then given by this, of course, and then you substitute the value we have now determined for K1, and then the controller transfer function is complete. So using the angle condition and the magnitude condition from the Root-Logos equation, we have determined the controller 1 transfer function. Now what's next is moving on to the other controllers, so controller 2 also. Now let's first again set up the controller 1. This is the expression. You can also write it down in different forms, so you can say, okay, I will work out these parentheses. That will give you a second order expression, polynomial. So s squared plus 7.54 times 2, and then also times s, and then the square of this 7.54. You divide that of course by s, and if you do also multiplication of this 3.28 for each term in the numerator, you will get this expression. You can also work it out and then make 3 separate terms, and from here you can determine that this will be the p, which is just a gain constant, and this will be 1 over s term, which is then the integrator part, and this is the times s term, which is then the differentiator part, and you can see here PID. That's why it's called PID. So there's the parallel combination of P, the I, and the pure D action. So the last closed loop transfer function now for our disturbance to output, so Y over D will be then this, we know that. And if I now substitute everything we have so far, the plant, the closed, the controller 1, which is our PID controller. If I now work out this by multiplying the numerator and denominator by s times s plus 1 times s plus 6, and you will get this expression, even working out these terms and make a polynomial, and you will get in the simplified form this one, so 6s over s cubed plus 26.7s squared plus 303s plus 1120. Okay. Now looking to step 2, which is consider only the reference input. Now the closed loop transfer function for that was already given again here, and we can now say let's define now for these two transfer the controllers as a new name, which is in a total controller just GC, which is the summation of GC1 and GC2. Then we have the following, just rename this, and then that will be then expressed in this form, because we know a lot of transfer functions here. Only the GC is unknown here and giving in red. Now we can again simplify this, multiplying the numerator and denominator by the s times s plus 1 times s plus 6. And this again can be rewritten in a form such that the denominator is a polynomial, which is exact same as the other transfer function from disturbance to output. Now the next step is using the zero placement approach. We have done it also in the previous examples. We know that the numerator of this transfer function must be equal or equated to the last 3 terms of the denominator of this transfer function. That is zero placement approach. So that means 6s GC will be then 26.7s squared plus 303s plus 1120. Now if you express now the total controller here, you will get this right hand side divided by 6s. Now if you work it even further, you divide by 6, so each term in the numerator can be divided by 6. You will get this expression, which is more simple. So 4.45s squared plus 50.5s plus 187, and that whole term will be then over s. We now know the total controller transfer function. We also know the controller 1 transfer function. Now we know the controller total is controller 1 plus controller 2. Then we can say the controller 2 is just mathematically seen. Controller 2 is controller total minus controller 1. Straightforward business. Then we can say controller 2 is controller total minus controller 1. We add up everything what we have so far. So this was what we have determined, and this was already determined in the previous slide, the discussion. If you work this out, you can see that 178 will drop off, because we have also here and also there. And this s squared terms, also s squared, s terms will be then in simplified form this. So you will get 1.17 s squared plus just 1s. And over s, of course. Now if you now work this out, you will get 1.17 s plus 1. And even more different written form, that you get the controller gain and also the zero. So you can see this is a PD controller. Why? There is a P action, so just the gain, and also the derivative action. And from this last transfer function form, you can see that there is a gain of this PD controller, and the location of the zero is also shown here, which is at minus 0.855. Okay, then we have now the total controller transfer function controller transfer function for the controller 1 and also that's for the controller 2. So we can now check our results. So the total result, again, this is GC1 and GC2. We have here our plant and the controllers we have designed. This for the controller 1 and this is for our controller 2. That means if you just substitute everything in here to write it out, you will get PD controller for the GC2 and PID controller for GC1. And here's the plant and the rest of the inputs and outputs. All right, let's then check what we have. So the simulation result, we need to check what we have achieved. We have now a plot which gives us the root locus plot, so the poles in the 0 location, also the locus, and we get the responses for the disturbance and also from the reference. Now this is the root locus plot. If you look at this pink dot, that's actually our or assumed dominant pole. So these two are the dominant poles. If you click on this location, you will see, or you can also see that from here because it is almost -10 and very close to -10, and this is very close to 8.0 something. So it is very close to what we have as a design point. If I now look at the plots here, and also first, let's also bring up our specifications again, the settling time and also the overshoot. You can see from here that this is the amplitude, which is, you can see 0.017, which is quite small if you just look at the input as 1. And also it approaches 0 rapidly, in this case in approximately 1.4 or maybe 1.2 seconds already. So that's fine according to specifications. But if this is done fine. So, but if I look at the unit step reference input response, the final value is 1, that is done, that's according to specification 3, that is okay, but the overshoot is 24.5%, that's not good because it must be 2%, so it is way larger. And the settling time is 0.568 seconds, and that is also larger than the 400 milliseconds, so 0.4 seconds was the maximum. So we need to tune in order to get this done, and much lower actually also for the overshoot. So we need to tune it and we need to see what we can do. So let's also look in great detail again what we have seen in the previous slide. This again our unit step response for our reference and also the disturbance here. So the blue one is the reference response and this is the disturbance response. You can see how much the difference is between the response from the reference and also from the disturbance. Again here, the specifications, this is definitely not good and this is also not good, but the steady state values are okay. And you can see here again a summary that we need to fix these red problems for overshoot and settling time. But the step response due to the disturbance is satisfied, is good enough. So we need to tune the controller. So we need to tune it, maybe just one or maybe more parameters. So let's start just with one tuning. So adjusting the controllers. Let's again summarize what we have as original controllers. These are the original controllers. This is the controller gain for the controller 1 and this is the 0 location. The other one is the PD controller. Now after trial and error in the control system designer tool in MATLAB, I have increased for the controller 1 just the gain from 3.28 all the way to 111.5, which is of course quite a lot increase, but that was already enough to do the job. And I have then adjusted controller 1 is this and controller 2 is not adjusted, that is exactly the same. So this is the only change I will make as a tuning, that is the gain of the controller 1 increasing from this value to that value. Then this will stay the same, PD controller, controller 2, but controller 1 will have a much larger gain. Now let's again see then what then the results are. So the root locus again and also response. This is now the root locus plot. You can see it has changed. So the poles actually are now moved all the way here, which are actually real, both real. And this is the response. You can see that the response, let's first start with the unit step per reference. Again, steady state value is 1. That's exactly okay. You can see also overshoot is 2%. So I went actually with this close to poles, the pink dots, all the way to a value for the gain such that the overshoot is exactly 2. You can of course lower that. And you can also see that the settling time is 0.0129 seconds. So it's 12.9 milliseconds. So way smaller than the 400 milliseconds, which is maximum allowed. So this is then very good, you know, in terms of overshoot is at the edge, but in terms of settling time is excellent. And you can also see that the amplitude of the disturbance also much smaller. So it is 44 times 10 to the power minus 6, which is also much smaller than what we had before. And again, the value decreases very close to 0 for the disturbance in approximately 1.4 or 1.5 seconds. Again, less than 2 seconds. All right, this is not the peak value, this is the peak value 0.004, so there's a mistake here. So much smaller here. Okay, moving on to the unit ramp response. That's also important. This is the plot. The orange one is the input, so that's actually a linear increasing line, and the blue is the response. You can see here, let me first bring up the specifications again. You can see here I've labeled for the ramp and also for the response here at time 0.4. You can see 0.4 seconds is the amplitude, also 0.4 for the ramp, because that's just a line with a slope of 1. But our response is larger, so there is an offset, so there will be some error. But in order to calculate if there is a steady state error, you need to check for the later stage. So at steady state will mean not at the beginning, but at a later stage. And if I now look at, for example, at 0.8, my ramp is 0.8 and my response also 0.8. In this case, there is no 0. That means the steady state error using these controllers for ramp is indeed 0, and that is according to the specifications we require. So we have 0 steady state error for unit ramp input. All right, moving on to the unit acceleration response, again from reference to output. This is the plot again. The orange line is what we apply, so R acceleration as an input, and a TYR acceleration is our response. Again, I have labeled some values here. Again, the specifications for our future reference. You can see at the beginning, again, there's some difference, so we don't look at the beginning at 0.4 seconds approximately. And again, took some arbitrary time, which is at 0.8, will give me 0.32 as a value for amplitude for the input, just a reference. And my response is exactly the same. That means it follows what I'm actually commanding as a unit step, unit acceleration, I mean input. So now we have also no steady state error for acceleration, which is then as required. And these are the transfer functions for the controllers, and this is the adjusted value. Okay, let's also compare the results for the simulation. We start with the unit step response from reference to output. The blue one is what we have what we get from the originally designed PID controllers and also the PD controller. By adjusting the PID controller, controller 1, we had this orange line. So this was red, that was not fine, of course. Then we have adjusted that, and it was done at 2%, and also the other one was much smaller. You can see also how fast this goes. So the orange line is indeed much better. And we also see that this final value for both of them are 1, so that is for sure fine. And this is the summary in the table, controller 1 and controller 2 for the original design controllers and also the tuned controllers. You can see the specifications here, the result, and also the values here for our tuned version, which is again according to the specifications. Okay, let's also look at the disturbance and see what kind of improvement we have by just adjusting the controller, because the reference to output response was not satisfactory. You can see here this was for the blue, which is the originally designed system response, and for the controller that is in this case much larger than this one. So this is then, let's say, 16.7 milli as the amplitude. In this case it is actually 0.40, let me check again, Yes, 0.44 milli. So this is way smaller than that one. And again, they also approach, let's say, 0 at approximately 1.4, maybe 1.2 seconds. So this is definitely much better in terms of amplitude, small amplitude, and this is also the final value. They are comparable. And again, the values here, you can see also the values for the peak value and also what they get, the final value as 0 after 1.4 seconds. All right, this is then for this example number 5, again, using step-by-step calculations, and also we have verified our calculations in MATLAB simulations. We've again seen that we need to tune something, but the tuning was quite easy because we only needed just one parameter to tune. Sometimes we have seen it in another example, example number 2, that we had also to tune another controller gain, so 2 controller gains. In addition, maybe also the location of another block or filter in your system, which is more complicated tuning. If you have any questions about this example or any suggestions, please let me know and I will try to answer them as soon as possible. Thanks for your attention, and don't forget to share and like this video so that we can reach more people for this very interesting topic. I see you next time, and take care.